Okay, well, let me welcome you to this 9th lecture of our course on reinforcement learning at ASU. Today, we're going to talk about a number of topics, all of which involve some kind of combination of estimation and control and dynamic programming, of course, and approximate dynamic programming. The topics are sequential estimation, Bayesian optimization, and adaptive control. They're all related, and they all share the feature that they can be addressed with a POMDP approach. We're also going to discuss an application to the wordle puzzle. Two of your colleagues, Siddhant and Amrita, they're going to come in at the end to discuss that. So here's the outline. We start with the estimation of a parameter vector, but sequentially, with a sequence of measurements, and the previous measurements are used to decide on the subsequent measurements. Then we're going to discuss Bayesian optimization. It's a subject of great interest these days. It deals with optimization of functions that do not have an analytical form. Instead, their values can be computed, but with a lot of difficulty and cost through simulation, through experimentation, so on. Then we're going to discuss the combination of estimation and control as it arises in the context of adaptive control. We will see that these two cases here are special cases of the adaptive control formulation, easier special cases. And then we're going to discuss the application of adaptive control for the online solution of the word puzzle, and we're going to use rollout for that. So sequential estimation of a parameter vector. We have a parameter vector theta, a multidimensional vector theta, which we want to estimate. And we want to use for this costly observations. And the number and the type of observations are subject to choice. There may be several types of observations that we can use with different costs, and we want to decide on which ones to use. So we have some kind of a system here that involves an unknown parameter. The a priori distribution of this parameter is known. We obtain measurements or observations related to theta, and the outcomes are evaluated by a decision maker who wants to decide between two things. One is to stop the observations and estimate theta on the basis of the observations that have been accumulated so far. And the other is to continue the observations, but select also the type of observation in case there are multiple types of observation. So this goes on for a number of periods, a finite number, or perhaps an unlimited number. And the number and type of observations are subject to choice. And instead, we have an evaluation of the observations by the decision maker with a view towards stopping or modifying the observation process. So this involves sequential decision making, thereby bringing dynamic programming to bear. Let me give a classical example of this. Suppose we have two hypotheses and we try to decide upon one of the two. And we do this by using observations that are costly and are sequentially obtained. And now, given a new observation, we can either accept one of the hypotheses, the stopping action, or alternatively, obtain a new observation at a certain cost. And the classical application of this has been statistics and quality control. Like we want to decide whether a certain batch of a product is acceptable or not acceptable. And we take samples of the product and test them out to see if they are good quality or not so good quality. And over time, we update the probability, the posterior probability, that the batch is defective or it is acceptable. And this was investigated in the 40s. And it was addressed by dynamic programming. Mind you, dynamic programming before the time of Bellman, okay? Dynamic programming goes way back. And there's a famous test that they came up with based on the dynamic programming formulation, the so-called sequential probability ratio test, which says roughly the following. Once the probability of one of the hypotheses being true rises above a certain threshold, then you stop the observations there and declare as true the hypothesis of that hypothesis. Otherwise, you continue the observations and keep going until at some point, you're almost certain that one of the hypotheses is true based on the probability, on the posterior probability. So that's a classical application. And there are other applications, extensions of this quality control type of application, statistical design, like select one of multiple hypotheses rather than just two, design of clinical trials, and test for medical diagnosis. So we make various tests until we're sure that, reasonably sure, that one of the diagnoses is correct. That's the hypothesis that we accept. Then there are sequential search problems, like search and rescue. We look over here, then we look over here, and then we have to decide where to look next, perhaps in places that we haven't looked so far, or perhaps places that are promising. Search and rescue is the type of typical type of application of this kind. Sensor networks. There is a network that we can go through and various measurements that we can take within the network. And we want to plan a route so that we collect adequate information for our purposes. So we go through the network and we look at one side of some target, let's say, and if we're not sure at what's happening, we may want to take a different measurement or a more costly measurement to supplement the ones that we had so far. Sequential decoding problems, and we're going to discuss this in the context of the Wordle puzzle. And then there is a surrogate and Bayesian optimization for minimizing black box functions. Functions that we don't have an analytical expression, but instead we can sample their values at various points. And we're going to discuss this one first. So these are applications of sequential estimation. And let me take the opportunity here to make an important distinction. The problem simplifies if the current choice of observation does not affect the availability of future observations or the cost or the quality. So if I take a measurement now, that doesn't mean that I'm not going to have the option to take other measurements in the future. This is the simple sequential estimation problem, and it's generally easier. A more complicated one is when once I take an observation now, that may preclude the options for the future. So this has more of the character of a control problem and can be viewed as a combined estimation control problem within the context of adaptive control. So we're going to talk about Bayesian optimization first, and the Bayesian optimization can be viewed as a special case of a broader subject, which is called surrogate optimization. Roughly speaking, we have a function that we can't, that we don't have an analytical expression for it. It's hard to compute it. So we construct, based on measurements, a surrogate function that we optimize instead. So the question is, how do we construct these surrogates? So the problem is one where we want to minimize approximately a function whose values at given points are obtained only through time-consuming calculation, simulation, experimentation. And the starting point is a parametric model involving a parameter theta. We consider models of this function, this target function that involve a parameter theta. We take observations that are related to theta, and then we decide either to continue the observations or to stop the observations with an estimate of theta, and therefore a surrogate, okay, based on this estimate. So we observe sequentially the true cost function at a few observation points. And then we construct a model of the cost function, the surrogate function, which by estimating theta, and we minimize the surrogate instead of the original to obtain a suboptimal solution. So the question is, how do we select observation points based on the results of previous observations? In other words, how do we make future observations more productive relative to our purpose? And generally speaking, a method of this type, a recurring theme is exploration versus exploitation, the trade-off between the two, which we have seen in the context of Monte Carlo tree search, if you remember. So what to express this sorry. To express this trade-off, what it is observing on one hand points that where it's likely to have near the optimum, points near the optimum. That's the exploitation part of it, or observing points that are in a relatively unexplored area of the search space, where we want to look into, hoping that we may get some good values of the function. Okay, so some example of surrogate optimization, geostatistical interpolation. A classical application of this was took place in South Africa in the context of gold mining. The names of Matheron and Kriege were engineers in South Africa are associated with this application. In fact, you'll see the name Krieging in the literature. Krieging is associated with Kriege. And the idea there was to find, to drill for gold in locations that were rich in gold. But how do we know that? Well, we have identified a certain area and we drill, make a few boreholes, take samples, test them, and then decide on new samples. But the drilling is costly. Therefore, we want to do this judiciously, and they came out with an idea that's very much like Bayesian optimization. And there have been several applications of this type, drilling for petroleum, things like that. Another class of applications, design optimization, where we use, in aerodynamics, for example, we use hardware prototypes very often. First computer prototypes, but then hardware prototypes that are taken in a wind tunnel. Now these are costly, and we have to test several of those to come up with a good design. And how you come up with a design is an issue based on the success or failure of earlier designs that may guide you new choices. Similarly, designs of new materials, design of new drugs, and so on. A more recent application, last 10, 15 years, has been in tuning of the hyperparameters of machine learning models like neural networks. A neural network, for example, has several parameters, right? The number of stages is a parameter, how big its stage is also another parameter, the other parameters. And given a data set, we want to design a neural network that will provide good estimates and use properly this data set. And therefore, surrogate optimization has been used in this context to tune the hyperparameters. And that has happened in particular in the deep neural network AlphaZero, allegedly. The AlphaZero paper talks about that, but doesn't give any details. So I'm not quite sure what they have done, but they claim that they have done it. And I'm not surprised because this is a common use of surrogate optimization these days. Okay, so now let's talk about Bayesian optimization. It's a form of surrogate optimization. And we have a black box function, a function which is not known, but we can obtain its values at various points, perhaps with some noise, at some substantial cost. So here we introduce a parameter vector theta, which has m components. The function is defined over m points, u equals 1 up to m. And we take as our parameter vector the values of the function at these m points, okay? Theta u is equal to f of u. So theta of 1 is theta 1, theta 2, and so on. So theta, the parameter vector, is the function itself. It is the function, the collection of values of the function. And we want to use measurements of the value of the function plus perhaps some noise, W, stochastic noise. And the noise could be 0. The measurements could be exact, but we're going to consider more generally the case where it's not exact. Could be exact as a special case. So here you see the picture. Here are the points where the function is defined, just 4 points here. In general, it would be a very large number. And it could be also a continuum, but we're going to consider the case of finite number of points in this lecture. The methodology for a continuum of points is similar, and but it's a little bit more complicated. I'm not going to get into it today. So this is the function f of u and its domain are these points here. And what we want to do is estimate theta, estimate the function itself with a number of measurements that's much less than the total number of points. In practice, f may be defined over thousands and millions of points, or perhaps an infinite number of points. But Bayesian optimization typically looks to find a surrogate within 10, 20, 50 points, okay? Because the measurements are expensive. The methodology is designed for surrogates with very limited data. So now the assumption we have is that we have an a priori distribution of theta, the values of the function. And this is called the prior distribution. It's B0. This is a probability distribution of a multidimensional probability distribution over Rm, right? Theta lives in Rm, m-dimensional space. So we have a multidimensional distribution over Rm, and the initial distribution is such that the values at neighboring points are correlated. In other words, we expect that points near to each other have correlated values close to each other. And how you choose the initial distribution is a little bit of an art. Generally speaking, people in Euclidean space, they take this distribution to have correlation, diminishing correlation for points that are further apart. So now, suppose that we have taken k observations at the points u1 up to uk of this type, the value of the function plus noise. Then we choose the next point at which to observe the value of f. We update the posterior distribution by using some estimator. All the statistics here of the prior distribution, the W statistics, probability distribution of W, they are known, so we can construct an updating formula for the posterior distribution that depends by the posterior distribution at k plus 1 is given by the posterior distribution at k, the new point where we take the measurement, and also the value of the measurement that we get. And now this bk is essentially the surrogate function. It's just a probability distribution of the values. It's a probabilistic surrogate function. And it is updated with each new measurement. Now, there's an important special case here, the Gaussian case, where B0, the prior, and the noises are Gaussian. Now, Gaussian distributions have a very nice property when it comes to estimation and regression. If everything is Gaussian, the estimates, probabilistically speaking, the posterior is also Gaussian. And there are nice formulas for updating. There are nice formulas for this BK estimator here. And so if B0 and the noise are Gaussian, BK can be updated by means of a formula like that, which has a closed form expression. And it's based on the theory of Gaussian process regression, which is a subject of its own. The thing that I want to impress on you is for the Gaussian case, this is relatively easy and admits a lot of help from closed form expressions. Otherwise, you have to implement this posterior updating. You may need a simulator, you may need particle filtering, and it may be more difficult. However, since we're not going to get into the formulas very much, but we're going to look into the principles of the approach, that will not bother us. So this is based on optimization. The parameter vector adjusts the function itself, and we update its distribution using new measurements. And we want to use measurements that are taken at points where they provide a lot of information. Okay, so let me give you an illustration here. What you see here is the true cost function, f of u. U is depicted on a line. F of u is the true cost function, right? The black. The surrogate, after a number of observations, 7 observations in particular in this case, which are noise-free, is this purple. It is a probability distribution. And it's depicted here in terms of its mean and its standard deviation. So the mean is over here at this point, u, and the standard deviation is shown here schematically, okay? So what are the observations here? There are 7 observations, 1, 2, 3, 4, 5, 6, 7. And the observations are noise-free, which means that they give us the exact value of the black function, right? However, at other points, there is uncertainty. And over here, there's a lot of uncertainty, similarly over here. And okay, so Bayesian optimization, we want to take some more measurements. Where would you look? Well, you might want to look around here, okay, where the purple function has low value. Or you may want to look somewhere where there's a lot of potential, perhaps, for decreasing the value of the function. That's roughly speaking the exploration trade-off. So we're going to come back to this figure. And now let's look at the methodology that's given that for Bayesian optimization. Most of Bayesian optimization is based on myopic ideas. The question, of course, is how to select sequentially the new observation point, given the observation results from previously selected points. And there is a principled way of viewing Bayesian optimization based on dynamic programming. I'm going to summarize it here. We introduce a POMDP model, partial state information model. The posterior distribution, given all the observations up to time k, is the belief state. UK, the choice of observation point, is the control. That's what you select. The belief estimator is the system, and we have the state evolving under the influence of control, and also there's some noise. The noise Z is the outcome of an observation at the point UK plus 1. And the statistics depend on both BK and also on UK plus 1. Now, the dominant method in practice is not dynamic programming. It is dynamic programming, but it's not explicitly stated. It is a greedy policy, which is based on an acquisition function. Greedy, and I also called it myopic because it looks only one step ahead as opposed to the prospects of getting additional measurements in the future. It doesn't look into the future. Now, what is this acquisition function? The acquisition function at time k is a function of the current posterior and the observation, a new observation point, in some measure of the benefit that you would derive by selecting the point UK plus 1 for observation when the belief state is UK. So I'm sitting at belief state UBK, I'm considering all these various possible measurements, and I compute this acquisition function, the benefit of choosing a particular control. And then I choose a control that minimizes or maximizes, in this case, by tradition, the acquisition function. So the myopic policy is to select the next point to observe to be the one that maximizes the acquisition function, which is defined for every U and also at the given posterior that you have. Now, there is an alternative method. When we have heuristic policy, we've learned that we can improve them by using rollout. And this is the alternative. You use rollout with a myopic-based policy so that we look into the future, into observations that we may be able to take into the future with advantage. Now this has been done. It has been advocated in several research works since 2016. And the results are promising, but there has not been enough testing of the idea and its variations so far. So now we're going to focus on the acquisition function and the base policy, the greedy policy. Okay, I'm going to look at some examples. By the way, are there any questions so far? Is it clear where we're headed?
How do you know when a surrogate is like within acceptable boundaries? How do you define the boundaries of the surrogate? That makes sense?
The boundary is up and down? Or...
Yeah, so like if you have a surrogate and it's kind of sits and it's like an approximation, how do you know, or how do you define what is an acceptable surrogate?
That's what I'm getting into now, okay? I mean, I'm getting into, how do you decide whether it's, okay? You decide often by running out of budget, okay? Another way to decide is sort of look at the variance at points, at areas of interest, the variance of the range of the surrogate. And if it's small enough, then you say, okay, I've done enough and I'm going to stop. Okay, so recall that the myopic policy at time k computes the acquisition function for every possible U and finds the one that maximizes acquisition function. And a common example of acquisition function is the so-called upper confidence bound, which is the sum of two terms, a TK term and an RK term. It's weighted with a beta parameter. Beta is some tunable parameter. And TK for a given U at the posterior BK is just the mean the expected value of f of u under the posterior distribution, okay? And RK is the standard deviation. So in this expression, this weighs both the mean and the standard deviation. And we can view the TK, the minus the mean, as an exploitation index. By maximizing this expression, we encode our preference towards exploring parts of the space where f takes low value, okay, based on the posterior distribution. RK can be viewed as an exploration index. It encodes our desire to search within parts of the space where there's a lot of uncertainty about the range of the surrogate, and therefore there's a lot of potential, perhaps, of getting good, good points to search. Now, this is one example. There are several acquisition functions in the literature. Another example is the expected improvement, where for every u, this is the expected value of the reduction in cost function that we are going to obtain relative to the minimum value of f that we have obtained so far, again, under the posterior distribution. So I'm going to demonstrate these two here in an example. And this one involves explicitly a trade-off between exploitation and exploration. Here, this also involves implicitly a trade-off, but it's not so apparent. But in fact, these two, as I will show you in this example, often give similar results. Okay, now I'm going to throw a little curve at you. I'm going to switch from minimization to maximization. This is a maximization example. This function here is the inverse of what I showed in an earlier slide. Now, why did I choose maximization? Because I found this example in Wikipedia, and I could not redraw it to make it minimization. In fact, in the Bayesian optimization literature, most authors prefer to use maximization rather than minimization. I could not find a good example with minimization, so I took the Wikipedia example. And here, what you see is the true function f, which is the black function. And you also see the surrogate, which is the posterior, based on 6 observations for this particular figure. So we have taken 6 noise-free observations, and we have observed the function at these 6 points: 1, 2, 3, 4, 5, 6. Okay? And we have obtained, through statistical considerations and statistical formulas, we have obtained this period. It has large variance here and relatively low variance here, but also we have the mean plotted here in terms of with this purple curve. And what do we do here? What does Bayesian optimization do? It calculates the acquisition function for all u. And here's the plot of the expected improvement acquisition function as a function of u, okay? So this acquisition function says that it's good to sample in this area, okay? The value of the acquisition function is large. And the expected improvement, okay, well, if you sample over here, there's no improvement based on the acquisition function because we have already obtained the best point to be over here, and we cannot improve. So these areas are excluded. And it is in these areas where you can get a potential improvement. And this is the plot of this acquisition function. And it's maximized at this point. So this acquisition function says sample right over here, okay? There's another acquisition function, the upper confidence bound, which weighs both the mean and the variance. It is plotted here. And it's maximized at this point. The 2 points are not identical, but they're close to each other. So I think in the Wikipedia example, the sampling is done with this expected improvement acquisition function. So the next sample, the 7th observation, is right at this point here, okay? So you see we got the exact value of the function at this 7th point. However, the posterior has also changed because of the new measurement, and it is what you see here, okay? So we started with 6 observations, got to 7 observations. Now we're going to go to the 8th observation. Are there any questions on this figure? Yes.
Yeah, so it's not very intuitive. So maybe you can motivate the intuition. So when I look at the graph, like to me, it seems like between the 3rd and 4th point is where there's sort of the largest discrepancy between the true function and the estimated function. So my question is, what is the motivation, I guess, behind this estimated, to estimate between the next set of points, as you mentioned? Because at least visually, it seems that if we sample between the...
Yeah, there's a lot of potential here.
Right.
But not really all that much potential relative to what we have gotten already, okay? Moreover, so the exploration potential is good, but the exploitation is bad. So these points are preferable according to both of these criteria, okay? Remember, we don't know how the function looks like here. We have no idea that there's a lot of, all we know is that there's a range of values of f along these points that we know this range. That's all we know. On the other hand, we know the range here, and the range is better than here, right? So it makes sense to search here. Now, after the potential of measurements in this region is exhausted, perhaps we'll come back here in future measurements, but not for the moment.
Right. But there's also like the beta parameter is also important in that case, right? Because you said that if we switch the beta parameter, then everything would change as well. It's just
the beta parameter is important. And I don't really know what is beta in these calculations of the Wikipedia example. I just couldn't find it there.
Okay.
There's a website that Wikipedia points to with a code, okay? So you can play around with the code, you can dig into it, but I really don't know what beta is here. Okay.
Thank you.
My question is regarding the acquisition function. Would the acquisition function take into account a point between all the 6 observations that we had? So to check by sampling which point would we get the maximum return? Like, is it dependent on the possible future points that could be sampled?
We have the acquisition function, and we have the entire purple graph here. We have it. We can sample it. We can obtain its values, the upper bound, the lower bound, in fact, the whole probability distribution.
Okay, so maybe
with calculations that I haven't described here, you can plot these acquisition curves here.
So it has no knowledge of any future points that could be observations?
No, only at the current, it depends only on the current posterior, the current purple curve. Given the purple curve and given a range of points, it will plot out, it will calculate the acquisition function based on expected improvement and based on any other criteria, such as the upper confidence bound and so on. So we can calculate these things and maximize the acquisition. We may have to use an algorithm to do a maximization of the acquisition function. But in principle, all of this is available to us to experiment with.
Thank you.
Okay, so after 6 observations, we selected this point over here, and we have obtained this posterior. Now we're going to play this game again. Here we are after 7 observations. This is the posterior that we gotten from the previous iteration. And what we do now, we have 7 observations. And what we do now is we calculate the acquisition function. For expected improvement, the acquisition function based on the upper confidence bound. They are again close. And the expected improvement prefers this point here. So, okay, I mean, it sees the best point that we have gotten so far is right over here. It sees a little bit of a gain, like 0.02 for this point. The upper confidence bound sees potential in exploration, right? And there's also exploration potential here, and you get a pretty decent values of acquisition function, but this point here wins. And I believe in the Wikipedia example, it uses selects the 8th observation based on the expected improvement. Selects this point and samples right here. Now these figures are not quite aligned here, so it may be, but the 8th point is right over here. Okay, it's this point here. Now we have wiped out the variation around here, and we have a lot of exploration potential over here. So let's see what the algorithm will do. Given the 8th observations, we have this posterior, and we calculate again the acquisition functions, and they both point to this area. Why? Because there's a lot of potential for exploration, basically. So we select this point here, and that's the 9th observation right here. Now our posterior became pretty good, okay? Starts approaching the real function. We have 9 observations. Again, we calculate the new acquisition function, and it points to this area as a good area to explore. And we have indeed taken this as the 10th observation. And after we have the posterior distribution, it's pretty good. And I have not gone to 11 observations, but already you can see where we started and where we ended up by targeting the right points to search for the value of the function. So that's the myopic approach towards Bayesian optimization. Like I said, it's the dominant approach. Has a lot of embellished variations for constrained problems, for problems with a special structure, all sorts of different acquisition functions and so on. Any questions?
So it looks like that the shape of the posterior, like after you sample one more point at the 10th of observation, like the purple region of the previously observed point also change. Is that because like the posterior is from like certain distribution family, and then like once you observe that big change, and it's assuming similar change in other points as well?
Yeah, you observe right here, but you don't. But the posterior does not change just in this region. Change everywhere.
Okay.
Because depending on the updating of the posterior that you have with Gaussian distributions, that will happen. Yes.
Oh, because it is from Gaussian distribution, so it assumes
right.
that the shape looks
similar. There's correlation of everything with everything else. It's just the degree of correlation changes with the Gaussian distribution, but there is correlation.
Okay, thank you.
Yeah. Okay. So now let's take a dynamic programming approach to Bayesian optimization. We formulate Bayesian optimization as a POMDP, where the state is the posterior and the control is the sampling point, and the noise is Z, the noisy observation that we get. And this is a dynamic programming formula. optimal cost to go at time k as a function of the posterior is the minimum over all possible u or over all possible observations of the cost of the observation. This takes into account the cost of the observation and the expected cost to go, conditioned, of course, on bk and uk plus 1. When you minimize with respect to uk plus 1, you get jk star of bk, a function of bk. And we start from some terminal time with a terminal cost function, g's of bn, a function of the state at time n, the final posterior. And this g function measures the quality of the surrogate obtained at the end. For example, it may value low means and small variances and things like that. Okay, so obviously this dynamic programming algorithm is impossible to carry out in as a practical matter. And the approximation in value space replaces J star by some J tilde. You may view this as a Q factor, an optimal Q factor. It is replaced by an approximate Q factor, where J star is replaced by some J tilde. Some function I haven't specified how it's obtained. So we minimize this approximate Q factor over all U, and that's the next point that we obtain. Now, defining J tilde is not so easy in Bayesian optimization, but people have experimented with rollout ideas, where J tilde k plus 1 is the cost function of a myopic Bayes heuristic based on an acquisition function. You simply run forward the acquisition function to obtain a Q factor, an approximate Q factor. It was proposed in 2016. There have been several papers afterwards. Consistently, all of them provide promising results, considerable improvement over the standard myopic Bayesian optimization approach. All of this is now under development, and I'm following it. I haven't done any work in this area myself, but I'm following it eagerly because it's an important area of research, Bayesian optimization. Okay, let me give you also a diagram of truncated rollout with a myopic Bayes heuristic. Remember, at time k, we have obtained all these observations. We have computed the posterior bk. We look at all possible next observations and at all the possible posteriors that this can lead to, okay? Now, this layer here is stochastic, so this tree is quite substantial. And then from the leaves of the tree, we do rollout simulation with the Bayes policy, the acquisition, the myopic policy, and perhaps truncate after a number of stages. All the studies that I have seen truncate after 4 or 5 stages. They look 4 or 5 measurements ahead. And there's also a lot of tricks that people use because this computation is fairly substantial here. They do use limited simulation. They use pruning, okay, to prune out some of the possible observations as being obviously. Perhaps you can use an acquisition function to prune out some possible observations that are really not promising at all. They look bad, okay? They're in bad regions of the space. We can prune those out. So that's where the research is at, and your class notes have references in this area. If you're interested, you may look into it. I think it's a very promising area of research. Are there any questions? Okay, so now I'm going to get into combined estimation and control and adaptive control, and then Siddhant and Amrita are going to talk about the word puzzle. Maybe we can take a break for like 5-10 minutes, and then we can do these things, these two subtopics together. So we'll get back at 535. Okay, so we have looked so far at estimation problems in the special case, sequential estimation problems in the special case of surrogate optimization, Bayesian optimization. Now we're going to look at a more difficult class of problems, which also involves estimation, but also control, like adaptive control. We have already discussed adaptive control, whereby we estimate unknown parameters of a system, and then based on the estimates, we apply control as if these parameters, the estimates were true. That's the indirect adaptive control approach. And we have discussed also the possibility of doing adaptive control by rollout. Now, I'm going to discuss now a more principled adaptive control approach that makes no a priori assumptions about the structure of the controller, starts from dynamic programming, and goes from there. So this approach is based on POMDP, and I'm going to focus on a rollout type of algorithm. We start with a deterministic system that involves an unknown parameter vector theta. Okay, notice that there's no WK. There is a corresponding analysis and algorithmic development for stochastic problems, but in this lecture, I'm going to focus on deterministic problems. I'm going to assume also that theta, the unknown parameter vector, takes 1 out of m values. In other words, the parameter space is already discretized, and there are m values. We just don't know what is the value. And we assume that theta has a known initial distribution over the m possibilities here and stays constant, doesn't change. In reality, in adaptive control, you have parameters changing, but it is hoped that as the parameters change, the algorithm also keeps track and is able to keep up with the changes. So theta now, we assume that the state of the system, xk, is observed perfectly, okay? Deterministic with perfect observation. And so this provides us some information about theta. By observing xk, we're essentially taking measurements of theta. And so that's where the estimation comes from. So we have the system, we observe the state. The controller accumulates all these sequence of all these observations and decides on a control using some policy that we are trying to find. Now, how do we formulate this problem as a POMDP? We have the state, it's observed, but then theta is not observed, and there's a belief state, however. There's an estimate, a posterior estimate of theta, which we can calculate. So we view theta as part of an augmented state. The state here is the pair xk and theta, and this part is imperfectly observed. This part is perfectly observed, and we plow in with Bellman's equation for POMDP, and I'm not going to go into the derivation, but this is the form. Remember that for POMDP, one possibility is to take as state the entire information vector or information state up to time k, which involves all the measurements, the states that we have observed, and also all the controls that we have applied. And the algorithm can be written as in terms of optimal cost to go as a function of the information state. And it takes this form. It involves minimization over UK of two terms. One is the expected value of the cost of the immediate stage, kth stage, which involves theta, but also is weighted with the current posterior of theta. So this term here is expected cost of the current stage. This part with the weighted with the posterior is the expected cost of the of the cost to go at the next information state, which is IK plus the new state, the new control, and the new state, which involves theta here. Now, this beta Ki is the belief state. It's a posterior distribution of theta over this M possibilities conditioned on the information that you have so far. So these are M probabilities. The probability that theta is equal to theta 1 or theta 2 or theta M. And we assume that this posterior can be generated online somehow by formulas or simulation. And it is used here in the dynamic programming algorithm. On the other hand, this algorithm is very, very difficult to execute in practice because it involves overwhelming computations. And so we consider the possibility of approximation in value space, whereby this J star is replaced by some J tilde. Now, the type of J tilde that seems, you can use anything as J tilde, but the type of J tilde that is useful in this context is one whereby there's dependence on the theta, and then there's dependence on the next state. So there's no dependence, direct dependence on IK and UK. And we use this in place of this. And we minimize over UK, and we obtain a one-step look-ahead policy. Now, there are some examples of J tildes here. One possibility is to select J tilde I to be the cost function of the optimal policy corresponding to theta I. Suppose we were clairvoyant and we knew the value of theta. Then we could design an optimal policy based on the known perfect state information problem. Suppose that we were able to obtain this optimal policy and then in its cost function. Then we could use this in place of that over here. Now, this approach has received a lot of attention in the past, not nowadays. It's forgotten now, but it was researched quite extensively in the late 70s and the early 80s. That was my time, not your time, my time. So I know this literature very well. And very prominent people have worked on this. It's an interesting approach for the following reason. Intuitively here, since you're getting a lot of measurements of theta, and the problem is deterministic, you expect that you will be able to zero in on the exact value of theta eventually, right? So you expect perfect estimation eventually of theta. And once you have perfect estimation, this approach here will give you an optimal policy for the POMDP, okay? So this is very seductive, very interesting, and looks straightforward, except for the fact, first, that you have to calculate an optimal policy for each one of those parameters. In some cases, this is easy. In some cases, not so easy. The second thing is that there are some hidden pitfalls in this approach, which all these researchers that I've talked about earlier have zeroed in and did some very interesting theoretical work. And they were able to overcome these difficulties, but there's a lot of interesting analysis and theory that goes with it. And the references are in your class notes, and you may want to look into them. Still, however, there is a problem of finding an optimal policy corresponding to every value of theta, and that can be overwhelming computation. And rollout gives another approach where instead of the optimal policy, J tilde is the cost function of a known policy, okay? Remember what rollout is. We have a base policy, we calculate its cost function, and we use it as J tilde. So that's what we use here. However, we have to calculate cost functions for every value of theta. The situation is simplified if we choose the same policy for all the, instead of using a different policy tailored to theta, we use a policy that's the same policy for all values of theta. And it turns out that, that you can prove a cost improvement property in that case. So this, in a nutshell, is the approach. And there are details here that you can find in the class notes. I just want to give you a schematic of how this rollout approach works. You are at the current state, okay? And you have calculated the posterior of theta based on all the information that you've gotten so far. Now you consider all the possible values of control as we do in rollout, and then we consider all the possible values of theta. There are m of them. In this particular figure, there's only 2 of them, but in general, there are m of them. And then you run the corresponding base policy up to the end. So what we do here is for every branch here, we obtain an average Q factor. This average Q factor involves the weighted sum with the posterior probabilities of Q factors computed, assuming that we know exactly what theta is. So for every possible value of theta, we calculate this Q factor. Pi I is the base policy. So we have to calculate this expression by simulation often. And so we calculate for every control an average Q factor of the control, and we minimize the, and we apply the control that has minimal average Q factor. So instead of using Q factors, we use average Q factors averaged using the posterior distribution. Looks pretty similar to what we had in the past, and it also turns out that you can show a cost improvement property. If all the pi i's are equal, the same policy, you use the same policy in all of these branches, then you can show cost improvement over pi. This requires an argument that's fairly similar to arguments that we have used in the past in the context of non-adaptive control. So in 2 slides, that's the theory. And now we want to go into the Wordle puzzle. It's an exciting project from last year. Siddhant and Amrita did this term paper project. And then it blossomed and with interesting results, and both in theory and as a practical application. Let me provide you with an overview, and then I'll turn to Siddhant and Amrita. Probably all of you know Wordle. Just about every person I talk to knows Wordle, and so many of them are dedicated players of Wordle. They play it every day, okay? Millions of people play Wordle every day. Wordle involves a hidden mystery word, or a code word, if you wish, that consists of 5 letters. The mystery word is drawn from an initial mystery list of, like in the New York Times version, about 2,500 mystery words. According to some distribution, in the standard version, the New York Times version, the mystery word is chosen according to a uniform distribution, but of course it's hidden. And the object of the game is to find that mystery word by making guesses. Now, as you make more and more guesses of words from another list, the guess list, the mystery list shrinks, okay? Because we use this information and the candidates for mystery word, the number of candidates diminishes. And eventually, when the mystery word list shrinks down to a single element, you have solved the puzzle. You have guessed the mystery word. And of course, the guesses are chosen based on feedback about the mystery word provided by the preceding guesses. There's a coloring scheme for which Dan and Amrita I'm going to talk about. And what we want to do here is a problem formulation, an optimization problem formulation, is to minimize the expected number of guesses to solve, the puzzle. Expected number over the probability distribution, the uniform probability distribution of the mystery list. Now, the uniform distribution turns out to be very critical here. The belief distribution over the current mystery list remains uniform through the solution process. In other words, these BKs, as they propagate over time, they remain uniform distributions. And this has been exploited by people who have solved this puzzle exactly, provided the optimal policy for the New York Times version. With this gigantic dynamic programming computation that took days and days with parallel hardware and so on. It was done by Selby, a British mathematician, in 2022. Now, without this uniform initial belief distribution assumption, then the exact solution would be absolutely impossible. Even with small variations of the problem structure, like increasing the mystery list or increasing the number of letters of each word. You would not be able to solve it in your lifetime by dynamic programming. On the other hand, rollout can solve near optimally, with very close to optimal, both the current version of the puzzle and also its variations online, much faster, in the order of seconds, maybe minutes, where you're talking about relatively small amounts of time. So that's all I want to say. And now I'm going to pass the microphone to Amrita and Siddhant for a more detailed description.
Okay. So Dr. Bhattacharjee introduced or gave a pretty brief overview of what the project has been about. And I'm trying to present, I'll go over a few basics, the preliminaries again, and please feel free to ask questions anytime. So we'll briefly revisit the POMDP model. We start with a finite set of states, and we assume there is a known termination state, which is cost-free. Then we have finite set of actions that will take us from one state to the other. There is a constraint subset that is dependent on the current state at step K, which essentially means that there are certain actions that we are assuming which are feasible at that stage. Of course, you could say that all the actions are possible at every stage, but just to constrain the subset of actions that we can take, or take only the valid actions which are possible, we just take this subset of the entire set of states. There is a deterministic transition function, because we are specifically dealing with deterministic POMDPs here, which is dependent on the parameter theta. And with respect to Wordle, when I'm explaining Wordle, I'll also say what these individual components imply in the context of Wordle and what essentially theta means in that context as well. And there is a cost function involved, which is also again dependent on the current state, the action taken, or the control in other sense, and the parameter theta. So just in case those of you who don't know what the Wordle game is, there's a small representation of me playing the game in a brute force way to make up this diagram. We have 6 guesses allowed. We start with any random 5-letter word that of course, the word needs to be a valid 5-letter English word. And the objective is to get to find the mystery word, which has by the end of the 6 guesses. So there are 2 modes of the game. One is an easy mode and one is the hard mode. The simple distinction here is in the easy mode, you have the complete flexibility to play any 5-letter word at any stage of the game, as long as you want to minimize the number of possibilities and reach the final mystery word. In the hard mode, in this example, you can see that once we get an observation, for example, I got the observation of the letter E in the first step, I have to necessarily use the words that need to be ending with an E, which essentially constrains a lot of like my subset of the actions that I can take at the next step. So that's pretty much the only difference. And yellow observation just stands for an alphabet that is correctly used, but at an incorrect position of the game. So that's pretty much the game. And the states here are the 2,315 words, which is the subset of the bigger list. And the final mystery word, for example, inert in this example, would be one of these 2,315 words. And the number of actions are essentially all the words that are possible in the game. And the simulator will accept those games, or those words. Then the transitions essentially in this context mean going from one mystery word list to the next. So for example, as soon as I played audio, I got the observation as I as a correct letter, but an incorrect position. My my actions significantly reduced to those number of words which have an I anywhere at one of the 5 positions. If I played the word stern, it will reduce to the words that have T and N at some position. And maybe this is the only word. Well, these 2 are the only words, but just as an example, T and N anywhere and E and R at these positions. So that essentially helps me reduce the action space based on the transitions and the observations that I'm getting from the game. And finally, the cost. So the cost here in this game is pretty easy as to how we are grounding it for our solution. When we utilize a guess word, we just take a cost of 1. And final state here, where we found the mystery word, would be cost free. And observations are essentially the colored observations that we are getting. So an important criteria to think about here was, before even we thought of why to use rollout here, we have access to the simulator. That's a huge advantage that we get out of this problem, at least, that we have access to the simulator. We can simulate what the observations will be hypothetically if we played a certain word as a guess word. So as Professor Bhattacharjee mentioned, there are optimal solutions. And this is a figure from one of the papers that, one of the articles that presented the optimal dynamic solution. The problem here being you need to have the optimal value function. The value function essentially will tell you, this is your current word. For example, in the previous example, I was at maybe audio. What is the value function if for taking the action turn with the current state audio? Is it the optimal choice to make or not? And for that, imagine the number of words you would have to search through, and also considering where that choice would eventually lead you to. So all those considerations need to be done. And the state space is enormous. As soon as, again, reiterating over the initial points made, the number of mystery words increase, the number of letters, maybe you start with a 6-letter word, this game would not even finish within months. So those sort of problems are natural limitations of the optimal solution using dynamic programming. So we try to approximate that value function. The function that you saw in the earlier slides that we were trying to calculate J star, essentially that was the optimal function. Now we are trying to approximate that by some J tilde. Now rollout is the solution algorithm that is helping us to compute that J tilde for any of the sets of actions and the theta parameters that we can take. So a slight deviation from the previous figure that Dr. Bhattacharjee showed. In this case, we have the same base policy. So as he mentioned, the results also show this, that if the base policy is same, we would have a cost improvement over the base policy when the rollout is also used. And I'll come to that once we look at the results towards the end of the slides. Does anybody have any questions so far? Okay, I'll move ahead. So what could be a base policy for Wordle? This is a snapshot taken from the famous YouTube channel 3 Blue 1 Brown's video. It was one of the first videos that actually became popular for playing the game Wordle. And the concept here, I use the snapshot just to explain the concept here, is to use information gain theory. What we are trying to do is calculate the entropy of a distribution. And that essentially is what we compute in what we calculate in entropy with the in bits essentially tells us how much is the search space reduced. So given a guess word, if I'm using, for example, the word crane, and for example, these are the different observations. So you could have 3 possibilities at any of the 5 alphabets, gray, yellow, or green, and which is why about 3 to the 5 observation patterns are total possible. Given crane, any of these 3 to the power 5 possibilities would lead to a certain final mystery word. And I know how many mystery words would fall into that. Maybe there are only 2.1% of the 2,315 words that follow this pattern. after crane is played. So that's exactly what information gain is telling me, that what happens if I take this guessword and based on the observations. So naturally, the idea, the intuition would be that I play the word that reduces my search space the most. And there could be many ways that you can actually try to minimize the search space with. The information gain is just one of the methods that has been very useful in practice. So I'll go over the algorithm, and this is at least the algorithm is presented in a very generalizable way for a deterministic POMDP. So what we have right now is we have the current state. We have the set of unknown parameters, theta. Sorry, I missed it. Theta essentially for us is the mystery word, because we don't know at any stage what theta could be. We have the current belief distribution. So at any time, whatever the possible set of mystery words are, we have a uniform distribution over them. So that is a very simplifying assumption over the game, which is what is true in the game as well. But to make it harder, you could definitely have a non-uniform distribution over the possible answers. And there is the action space, the transition function, cost function, and the base policy cost function, which we are essentially going to use the information gain for. So we start with an empty average Q list, which we are going to store all the Q factor, the average Q factor values for any possible action that we can take. And for the rollout part, for each individual theta that is possible, which means that each individual mystery word that is possible, I'm going to iterate over. We calculate the Q factor. So the Q factor for that, Q factor dependent on the theta as well as the action, the next step action would be dependent on the cost, which is just like, if I'm playing this word, that would be like cost of 1. And what could be the total cost till the game is terminated. So that is the value that J will give me eventually. And then I just append it to my list of Q factors for this particular theta. I find the average Q factor. The average Q factor here, now since this is in generalizable, I denote it as the product of the posterior distribution with the Q factors. In this case, it would just be a mean over like 1 over the number of mystery words that are possible over the Q factors, sum of Q factors. And then eventually we choose the one that is minimizing these Q factors and apply it to the transition function to get the next state. So that is how at least the rollout with using the base policy function can be utilized here. Too many numbers, but to get the gist out of this, I have a few opening words that were deemed by different people who tried solving the game based on different algorithms, different base policies, I would say. One was information gain. The other could be character frequencies. You try to see and match the character frequencies and so that the search space is reduced. So that could be one of the ways. So these are 10, I guess 9 or 10 words. And I use the maximum information gain as the base heuristic. These are the optimal scores that we already have access to from the optimal function. The good idea here is that we can see how much the deviation from the optimal score is if we just use the base policy and if we use the base policy with the rollout improvement on it. The percentages essentially help us to understand how far the optimal scores are for how far the rollout scores are from the optimal score, as well as if we just use the base policy. So it's very straightforward to say that the improvement is very significant. Another interesting point is we actually experimented with 2 more heuristics. One was called the MRD, which was the most rapid decrease base policy. And the other one was greatest expected probability. So I'll give a gist of what they are before I go for explaining this figure. The most rapid decrease algorithm essentially saying that if you're playing a word, you would lead to a certain set of possible words that could be the answer. Now, based on those 3 to the power 5 observations, each of the observation could lead me to a different set of those possible words. That could be the final answer. I'll just choose the word that leads me to the smallest set. So that's one way of reducing your search space. The greatest expected probability is I'll try to find the probability, just an approximated probability rather, of each word being the final answer. So again, that is also an approximate heuristic to get to the mystery word. Now, what we tried was we experimented just to have some empirical results on this, on what we were trying to hunch on using the rollout. The improvement, so the Y-axis shows the average number of guesses, which is average number of guesses to solve the 2,315 words. X-axis shows the number of the star. And all the line plots with the crosses are essentially the line plots for the base heuristics, and the ones with the dots are the ones with the rollout. So the line plot with the crosses for yellow, which was the GEP heuristic, does not exist because all the scores here that I haven't shown here are above 5, are in the domain of 5 and 5+ average number of guesses. The interesting part, the takeaway from everything that I've been ranting about so far, no matter how the heuristics are performing individually, there was GEP heuristic which performed extremely bad as compared to the other two. We had the maximum information gain heuristic, we had the MRD heuristic. The rollout improvement gets, the line plots for rollout improvement are much lower than their corresponding base heuristics, and pretty much closer to the minimum that was possible if I'm saying that maximum information gain was pretty much the best heuristic that I could have used. So even if the plot for GEP was too bad, the rollout plot for that is pretty much still closer. So that cost improvement is what I'm trying to show here. And the best case was for the word salad, which essentially the optimal score was 3.5084. And the closest that we could get in the range of 0.4% of that score was using the maximum information gain heuristic. So the cost improvement property becomes very evident using this plot. But there are certain limitations to take care of when we are trying to look at what the rollout can do and cannot. There is an important need for a reasonable base policy. Now, in our case, the idea was not to see which base heuristic was better, but it was to see, given any reasonable base heuristic, what could rollout change about it? What was the improvement that the rollout could bring about it? So at least it was relatively insensitive to the base policy, but there could certainly be cases where it does not show a very significant improvement. Then there is a need for a posterior distribution estimator. The game simplified it for us in this case because the distribution was uniform, but you would definitely need something like a particle filter algorithm so that you can know what the posterior distribution would look like if you don't have any intuition about it. And the number of Q factors. Now, number of Q factors could enormously, that you need to compute could enormously increase if the number of states increased or the action space increased. But there are certain techniques, for example, pruning techniques that you could reduce. For example, you would not use all the actions to compute the Q factors for. You can just take maybe the top 10 or top 100 performing action words and say that maybe the best next action could belong to one of those. Offline training using a neural network, pretty much closer to what AlphaZero had, because essentially you have a network that is trained upon given any state and a corresponding action, you can see what an approximate Q factor would look like for it. So if you do not have access to, for example, I could directly compute the information gain for any action or any guess word given the current state. But if I could not, for example, the base policy was difficult, I could have trained a network. I mean, just to overcomplicate things, I could train a network just to learn the information gain heuristic as well. That could be overcomplication of things, but that is one possible way if you would want to compute the Q factors in that way. So in summary, we talked about a dynamic programming based online rollout strategy. And the solution is applicable to deterministic POMDPs, which have this unknown parameter. And the most important reason for having this approach is exact solution may be intractable in a lot of cases. We demonstrated this approach empirically using the popular Wordle puzzle. And at least I believe that working around games and showing some algorithmic improvements using games seems to be pretty interesting and to easily understand and to discuss with other people as well. And it definitely provided near optimal performance and impressive improvement over the heuristic approaches. And the key limitations that we were able to identify that I discussed earlier were also through this set of experiments that we carried out. So that's all. I'll be happy to take any questions. And there's a very detailed arXiv preprint that we have. So if you want to check out, with a lot of theory that is associated with this as well, along with the experiments. So please feel free to check that out. Thank you.
Thank you for the presentation. My question is, like, I have a question like that is kind of related to what we are like, what is taught in today's lecture too. Is that like exploration versus exploitation thing? I remember that people, according to statistic, there is like an optimal opening word that you can like for me, that information gain thing looks more like an optimal exploration because you are looking for more information like from the guests. But is it possible to switch in between like different policy, like say like you are at the third step, you would want to give it a shot or something? Like when, for example, you think you have enough information for a shot or something like that. Because like the baseline currently looks like you are just trying to explore to the end until you like narrow it down to a very high level that the P of X is very high, right?
So if I'm understanding the question correctly, are you saying we can switch the base policy in the middle?
Yeah, like because for me the information gain is quite light towards exploration, I would say. But like at certain step, after certain step, you would want exploitation because like if you don't give a shot, like you can guess the word, right?
So, okay, here's the thing. Based on my understanding on the information gain heuristic, it would eventually lead you, I mean, exploration and exploitation would be very overloaded terms in this context because, let me try to explain that. In the beginning, you would have too many words to explain with. I agree, it's very intuitive having an heuristic like information gain, which would reduce your search space. But towards the end, even information gain would lead you to a single answer at the end. So when do you even say that the exploitation began? I mean, I don't really see the distinction of using those two terms in this when you are actually rolling out the policy.
Oh yeah, because the posterior is uniform, that like you don't have like certain words having higher frequency than others.
Right, right.
I see. Thank you.
An exploitation geared base heuristic would try to select guess words that are most probable, okay? So you have great probability to hitting the mystery word in one shot. On the other hand, like you said, the posterior distribution is uniform over the current list of eligible words. So this is not possible. On the other hand, in general, in these problems of POMDP adaptive control, there is a possibility for exploitation type of policies or in using exploration type of policies. And a handy idea in this respect is if you have a policy that's strong on exploration and another policy that's strong on exploitation, you can put them together and run them both and then take the best of the two, right? We talked about parallel rollout, where you have multiple heuristics. So it's a possibility to do that.
Any other questions, guys? Okay, let's thank Siddhant one more time.
Thank you, Siddhant. And I'd like to close this lecture with a couple of announcements. There will be no lecture next week. In fact, we have come close to the end of the lecturing portion of this course. And I want you to focus on your term papers in the last month and in the following month and a half. I'm going to give a couple of lectures after next week, 1 or 2 lectures on neural networks. Now, remember that your class notes have 3 chapters. One chapter was sort of a foundational overview of the field. Then a second chapter was focused on rollout and its various forms, deterministic, stochastic, minimax, and so on. And the third chapter has to do with approximation, of cost functions and policies by using training and neural networks. That's also a very important part of the reinforcement, the learning methodology. And in fact, we have touched upon it in passing at various points in the course. So I want to spend 1 or 2 lectures on training neural networks, training approximation architectures, and also how you use these trained architectures in the context of online play. So that's what remains in the way of lecturing. And then turning to term papers, I've received over a weekend a deluge of proposals, very interesting, okay? A very interesting collection of proposals from many of you. And I look forward to reading some more about them and also look forward to working with you. And if you have some questions, either in response to my communication to you or in response or just your own, get in touch with me, and hopefully some of these ideas can be developed and into something nice. Okay, so we'll see you in 2 weeks.